Welcome all of you. In previous session, we discussed about the thermodynamic requirement of a reaction and kinetic requirement of a reaction. We had also discussed about the entropy of activation. Now in the same point, we see the detail of entropy of activation, how entropy of activation affects the rate of a reaction. So with examples, we discuss the entropy of activation. So as we know, for a reaction to happen, the reacting species must come closer to each other in a specific orientation. For example, suppose E2 reaction, elimination reaction. So for example, suppose we have a substrate like this, R1, R2, R3 and R4, and for an elimination reaction a base is required. So suppose we have a base OH minus. So if we consider a substrate, this substrate, so this substrate have different types of conformations, but for a reaction to happen, the substrate must come in such a orientation that the OH and OTS should be trans to each other. Getting this? Also the base must come closer to this H plus in a specific direction. Getting this? So for a reaction to happen in a transition state, both the substrates have to surrender their degree of freedom. As we know that these conformations have different types of conformations, but for a reaction to happen, it should be in this conformation where hydrogen and OTS tosylate group, that is an eliminating group, must be anti to each other. Getting this? So here this substrate lost its degree of freedom, and only one type of conformation the reaction happens. So as there is a loss in degree of freedom, there is a loss in entropy. So for this reaction to happen, see what is the mechanism here? The base abstract this proton, this bonding electron pair comes here and form a pi bond, and OTS group, tosylate group, is eliminated. So after reaction, what we get? We get a olefin. Okay. So here what we observe that? We observe that for this reaction, the degree of freedom of reacting species is lost, and therefore the entropy of activation is also lost. That means we get negative entropy. Okay. So now we go for the next point and consider that how the entropy of activation affects the rate of reaction. First, when we study only one reaction, we can find out only the rate of reaction of a particular reaction, but for understanding whether the reaction is faster or slower, we have to consider two similar reactions. So now we consider different examples and compare the rate of the reactions. Okay. Now the first one is the ring closing reaction. Ring closing reaction. Okay, now we consider two similar substrates for a ring closing reaction and we compare the rate of reactions of that substrates. For example, we have a 10 carbon chain compound and we take another substrate of 6 carbon chain compound. Now for a ring closing reaction to occur, the two ends, that is X end and Y end of the chain must come close to each other. Getting this? So we number these as a substrate 1 and we number these as a substrate 2. Okay, here also for substrate 2, when ring closing reaction occurs, these two ends must come close to each other. And in this case, in the substrate 1, as it is 10 carbon chain substrate, there are number of or different types of conformations possible for this conformation, for this compound 1. But for a ring closing reaction, only few of the conformations are there in which the two ends of the substrate, that is X end and Y end, come close to each other. And in other conformations, these ends are not close to each other. So for a reaction to happen, the substrate has to lose its all other conformations except only the conformations in which X and Y ends are close to each other. Okay. So here, in this case, in case of substrate 1, it is having more number of conformations as compared to conformation 2. In conformation 1, only few of the conformations are there in which X and Y are close to each other, and then ring closing reaction happens. So most of the conformations of compound 1 has to lose. That means the degree of freedom of compound 1 is lost more as compared to compound 2. In case of compound 2, the loss in degree of freedom is less as compared to compound 1. So here the entropy of activation or loss in entropy of activation, that is delta S hash. In case of compound 1, the loss in entropy of activation is more and loss in entropy of activation here is less. Getting this? So here the rate of reaction of compound 2 is faster as compared to the rate of reaction of compound 1. Okay. Now we consider another example of ring closing, where we consider a formation of ester. Suppose we have two substrates. In one substrate, the acidic group and alcoholic OH group are in one substrate, and in other reaction we consider the two separate acidic substrate and alcoholic substrate. That means we consider here two types of reactions. One is intramolecular and another one is intermolecular reaction. Okay, so suppose we have the substrate like this. On treatment with acid, the substrate on treatment with acid, it is acid catalyzed ring ester formation reaction. So it undergoes the ring closing reaction and a lactone is formed. Okay, so this is one reaction. Another reaction we compare where we take two separate substrates. One is acid and another one is alcohol. This on treatment with acid undergoes formation of ester and gives the compound 2. Okay, we number this, the compound 1, compound 2. And here we number this substrate as A, this as B and this as suppose C. Okay, now we consider the rate of reactions by comparing reaction 1 and reaction 2. In case of reaction 1, since both the reacting species, that is acidic group and alcoholic OH group are present in the same substrate, so here they lose its degree of freedom, but the loss in degree of freedom is less for a reaction to happen in a transition state. But here the substrate B and substrate C, there are two different substrates, and since there are two different substrates, each substrate has its own degree of freedom, and in order to happen a reaction, these two substrates has to lose its degree of freedom. So loss in degree of freedom is more in reaction 2 as compared to in reaction 1. So this reaction is an intramolecular reaction and this one is a intermolecular reaction. Okay, and loss in entropy of activation is, in case of reaction 1, since there is less loss in degree of freedom, the loss in entropy is less, and in reaction 2, each substrate has its own degree of freedom, and for a reaction to happen, we know that the reacting species has to come in a specific orientation. So degree of freedom, or here the loss in degree of freedom is more in reaction 2, and therefore the loss in entropy is also more. So which reaction is faster? In this case, the reaction 1 is a faster reaction and the reaction 2 is a slower reaction. Okay, now we go for the next example. Next example before going to a next example, we have to conclude that what we conclude here, the intramolecular reactions, the entropy of activation, loss in entropy of activation is less for intramolecular reaction and loss in entropy of activation is more in intermolecular reaction. Okay, now we go for a next example. We consider a unimolecular pericyclic reactions. Okay, so we consider here a Claisen rearrangement. A Claisen rearrangement, as we know, require a thermal condition. So here, suppose we consider a substrate like this. Okay. So this substrate is a allyl vinyl ether. So allyl vinyl ether on heating undergoes a sigmatropic type of rearrangement, and we get the formation of product like this. Okay, so this is the product formed in this reaction. Getting this? So, in order to consider the rate of the reaction, we have to consider the loss in entropy, or we have to consider the degree of freedom of the substrate in transition state. So, these substrate, allyl vinyl ether, have different types of conformations. For example, like this. Okay, or like this. Okay, so these are different types of conformations which the allyl vinyl ether shows. There are many more conformations, but in order to get a product, the substrate in a transition state must come in such a orientation that these two ends come close to each other. That means this allyl vinyl ether has to come in a 6-membered transition state. So when it comes in a 6-membered transition state, its all other conformations are lost. That means its degree of freedom is lost, and therefore the entropy of activation is also lost. So here we get a negative entropy of activation for such reactions. Okay, so for this reaction, the entropy of activation is minus 8 kilocalorie per mole. Okay, now we go for the next example. We consider a next example, a Diels-Alder reaction. In a reaction where the two substrates total number of molecules decrease in a product are usually attended by a negative entropy of activation. Okay, so with example we see a Diels-Alder reaction. In Diels-Alder reaction, as we know, the substrate used is a butadiene and a in substrate. So suppose we have malic anhydride and butadiene. So here the product is, for this reaction, is like this. Sorry. The product is like this. Okay. So here in these type of reactions where number of reactants decrease, suppose we have 2 reactants and in the product we get only one reactant or only one product. That means the number of molecules going from reactant to product is decreased. In such type of reactions, the entropy of activation is lost or entropy of activation is also decreased. So here you can see the butadiene. We know that the butadiene is also having the conformation like this. Okay. Also like this. Okay. So these are the two conformations of the butadiene. But in order to happen a reaction, the butadiene must be in this conformation and not in this conformation. So here the degree of freedom of butadiene is lost in a transition state. Okay. So therefore here the entropy of activation value is negative. Okay. Now we consider another example of such type where the number of molecules decrease in the product. For example, consider addition reaction of halogen to olefin. Okay. So here, suppose we have a olefin, okay, and a general halogen molecule we take X2. So the addition of X2 to this olefin takes place in anti-fashion. Okay, so the product obtained is like this. Okay, since it is a stereospecific reaction, in order to obtain this anti-product, the substrate has to lose its degree of freedom and has to come in a specific orientation in order to get this anti-product. So here also the we observe loss in entropy of activation. That means the entropy of activation is negative in this type of reaction. Okay. Now we consider one more example for this. The entropy of activation for this is the SN2 type of reaction. Okay. The next example is SN2 type of reaction. So in SN2 type of reactions, the transition state is highly crowded, and the highly crowded transition state shows a loss in degree of freedom. That means a negative entropy is observed for SN2 type of reactions. So suppose we have a ethoxide ion reacting with a alkyl halide so here in a transition state, see the transition state here is highly crowded. Okay. So since transition state is highly crowded, the degree of freedom of this alkyl halide molecule is lost. Okay. So as the bulkiness of this R group increases, there is more and more loss in degree of freedom of alkyl halide. Okay. So here when R group is hydrogen, the entropy of activation is 9.5 calorie. While when R group is tertiary butyl group, the loss of entropy of activation is 20 calorie. So these are the so negative values, minus 9.5 and minus 20 calorie. So here we observe in SN2 type of reactions, we observe a negative entropy of activation. That means there is a loss in entropy of, there is loss in the degree of freedom of a molecule. As the bulkiness goes on increasing, there is more and more loss in degree of freedom. So this value, entropy of activation, becomes more and more negative. Okay. Now we consider one more example in which from one molecule we get ions in a product. For example, consider a alkyl halide. Alkyl halide on ionization reaction gives R plus and Cl. Suppose RCl, so it gives R plus Cl minus. Okay, so here what we observe that from one molecule we get two ions. Okay. Okay. Now we consider next example in which we see the reaction where from a one molecule we get formation of number of ions. For example, solulysis of tertiary butyl chloride in aqueous ethanol. Solulysis of tertiary butyl chloride in aqueous ethanol. In this reaction, the tertiary butyl chloride on solulysis gives a tertiary butyl cation and a Cl minus ion. This tertiary butyl cation is written, is actually the structure is like this. Okay. So from this reaction, we expect that the positive entropy of activation. Why this is? Because from one molecule in a product we obtain two ions, and each ion has its own degree of freedom. So here degree of freedom increases in the reaction, in the product. So we expect what we expect? We expect that there is increase in the entropy. But practically what we observe that the entropy of activation of this reaction is minus 6.6 calories per mole per degree. Okay, minus 6.6 calorie entropy. The negative entropy of this reaction indicates that there is loss in the degree of freedom of the product ions, and this loss in degree of freedom is due to the solvation of the ions in this reaction. So here see how the solvation takes place. Suppose the tertiary butyl cation in ethanol, here the solvent is aqueous ethanol. So in ethanol, it forms the solvent molecule forms a van der Waals force of attraction with this positive ion. And since there is this type of interaction is observed, the degree of freedom of this cation, tertiary butyl cation, is lost, and therefore the entropy of activation is negative. Also similarly, the chlorine Cl minus ion also solvated, in this case with the solvent molecule. Like this. Okay. So here also the degree of freedom of chloride is lost due to solvation by the solvent molecule. Okay. So this is about how we obtain or how we compare a rate of reaction by studying the entropy of activation of a reaction. Now one more example we see where from a ordered starting material or ordered reactant we get a disordered product. That means from less degree of freedom we obtain a product having more degree of freedom. For example, a ring opening reaction. Ring opening reaction. Suppose a cyclopropane, when undergoes a ring opening reaction on heating gives CH3CH double bond CH2. Sorry, CH3CH double bond CH2. So what we observe here in this reaction, more disorder in transition state is observed as compared to a reactant, and the entropy of activation of such reactions is positive. Okay, the reaction with more positive value of entropy of activation is having faster rate of reaction, and the reaction with less positive value of entropy of activation shows less or slower rate of the reaction. Okay, so this is about how the entropy of activation is important in considering or while studying a rate of a reaction. Thank you.